So how do all the quantum numbers fit together? You've been introduced to 4 different quantum numbers, N, L, ML, and MS. Now these can be confusing because there's a lot of different words that people use to describe them. N can be called the principal quantum number, it can be called the energy level, those are probably the 2 most common. But what is important besides that is that N describes the distance of an electron from the nucleus. So if you imagine this as the nucleus, an electron this far away might be described as being in N equals 1. An electron this far away might be described as being N equals 2, and so forth. The further away you get from the nucleus, the higher the principal quantum number, or the bigger the number associated with its energy level. That's because the further the electron is from its positive nucleus, the more energy is in that system, and the less stable it is. The next quantum number, L, the shape of the orbital, can also be called a sublevel. If you've heard that terminology before, it can also be called a subshell. What this is it describes the shape of the area that the electron inhabits. So it can be the shape of the electron itself, because quantum mechanics is weird, or it can be described as the space which you might find the electron if you're thinking of it more as a particle. So in the L, these can be used to describe these, we can use either a letter or we can use a number. When we talk about quantum numbers, we tend to use numbers. Later, as we talk about electron configurations in Chapter 8, we'll tend to use the letters more often. So, if L equals 0, then this can also be called an S sublevel. If L equals 1, this can also be called a P sublevel, and if L equals 2, then this can be called a D sublevel. If L equals 3, we call it F, and so forth. So we will focus on S, P, and D, although we will talk a little bit about F as well. Now, the L describes the shape of the orbital, right? So an L equals 0 or an S orbital has a spherical shape. An L equal 1 or a P sublevel has a peanut shape. And an L equals 2 or a D has kind of this like clover or flower shape like this. Then we can talk about the ML, the orientation of the orbitals. So the L up here can sometimes be called the sublevel, and the orientation can be called an orbital. Now an orbital is just a word that describes like the area that the electron is in, or the wave function of all of the area of the electron itself. Now the orientation of the orbitals depends on which sublevel it's in. So if L equals 0 and it's in the S sublevel, that means it's shaped like a sphere. If you imagine yourself holding like a soccer ball, now turn the soccer ball 90 degrees. How does the shape change? The shape of a sphere, no matter how you're holding it, stays the same, right? So that means we only have one option for M equals L, and we call that 0. We start at 0 for L, we start at 0 for ML. For N, we start counting from 1. Don't ask me why, I didn't come up with the system. Okay, so for L equals 1, now we have this peanut shape. So you're holding a peanut, imagine it like that. Now you turn it 90 degrees. Has the direction of that shape changed? Yes, there's 3 different ways that you can orient a p orbital. You can orient it like along a y-axis, along an x-axis, or along a z-axis. Now each one of these is going to be associated with an ML value. So the ML for one would be 0, for another one would be -1, and for another one might be +1. Now the +1 isn't associated with the z-axis necessarily, but what's important is there's 3 different ways you can orient a p orbital, and so we have 3 different ML values. We start at 0, and then we count down and we count up until we have a total of 3. For L equals 2, I'm running out of space, but if L equals 2, we have that clover shape. There's actually 5 different ways that you can orient a d orbital. Now I don't expect you to be able to draw all 5 of these, but you should be able to recognize which ones are d orbitals. So you should be able to draw the L equals 0 and the L equals 1, but I don't expect you to be able to draw the L equals 2, although I do expect you to be able to recognize it. And lastly, the MS just describes this direction of the spin. So each one of these is called an orbital, and in each orbital you can only have a maximum of 2 electrons. And in order for both of those electrons to be the same space, they have to be spinning in opposite directions. And we usually represent electrons by arrows, and we represent their spin by an up arrow or a down arrow, and they have to be opposite to be in the same space. So to put all of this together, here is a diagram I like to use. So this here is an n equals 3 energy level, or this is the level described by the principal quantum number 3. Remember, what does that 3 mean? N equals 3 talks about how far away from the nucleus these electrons would be. So that means they're on like the third level away from the nucleus. So if you're thinking about it like a ladder, these are on the third rung. Now, so this whole thing, all of these boxes here, are describing the n equals 3 energy level. Now you'll notice there are groupings here. There's a group here, a group here, and a group here, and these are describing the sublevels, or the L quantum numbers. We have 3 in n equals 3, so whatever the number of the energy level, you have a maximum of that number of sublevels. So in n equals 3, that means we can have 3 sublevels, or 3 different L values. Now L starts counting from 0, so we have an L equals 0, we have an L equals 1, and we have an L equals 2 sublevel. This is our 0, this is our 1, and this is our 2. Now remember, those correspond to an S sublevel, if you've heard that before. If not, we'll talk about it next week. A P for L equals 1, and a D for L equals 2. What that L is telling you is what shape it is in. So an S sublevel has that spherical shape. There's only one orbital in the S sublevel because it has only one way that you can orient it. The P sublevel, or L equals 1, looks like a peanut, right? And remember, there's 3 ways that we can orient that peanut in space, and so we have 3 orbitals associated with our L equals 1, or our P sublevel. The D looks like a clover, and remember, you don't have to be able to draw these, so don't panic. You do have to draw these two, the S and the P, but not the D. So we have our different sub-levels within them. What's the next quantum number? And ML describes not the shape, but the orientation. So the shape of the S is a sphere. There's only one way to orient it, so that means NL is equal to 0. When we move over to the L equals 1, or the P sublevel, there's 3 different ways to orient it, so that means we should have 3 different ML values. The way I like to do this is start with a 0 in the middle, and then count up and down until you've covered all of the boxes. And for the D, we start with the 0 in the middle, so then we have a -1, -2, +1, and +2. So 5 different ways you can orient it in space. So with each increasing sublevel, you add on 2 orbitals. So how many orbitals would there be in the F block? You have 7 orbitals, because it's going to be 2 more than the D. So what this means is, if you have an electron in the 3rd energy level, that electron could be here in the S. You could have a total of 2 electrons in the S block, and they would be occupying a spherical shape around the center in the 3rd group out. Or your electron could be in any of the 3 orbitals in the P subblock, and then they would be occupying a space that looks something like this in the 3rd energy level out. Now you could have 2 electrons per one of those, or it could be in the D block, and then it could be occupying any one of these weird shapes like this. We will talk more about how to describe the location of the electrons starting next week, but that's how all these different quantum numbers fit together. And the purpose of these quantum numbers is just so we can understand where the electrons are in an atom. Because all of chemical reactivity, except for nuclear chemistry, comes down to where the electrons are. This is a really, really powerful model for us to understand how different atoms will react in different situations.